So I would like to welcome you in this workshop. So good morning, afternoon, or evening, everyone. So thank you for joining us in this workshop organized under the scope of the EMPIR project rhoLiq, dedicated to the establishment of traceability for liquid density measurements. So, as you may know, the rhoLiq project was carried out with the funding of the European Union under the EMPIR. This program is jointly funded by the EMPIR participating countries within Eramet and European Union. So my name is Andrea Furtado, and besides hosting today's workshop, I'm also the project coordinator and the head of Property of Liquids Laboratory at the Portuguese Institute for Quality. So concerning today's agenda, this workshop will be divided in two main parts. The first one, or before lunch part, rhoLiq project and IPQ research activities will be presented, followed by the theory, methodology and robustness studies of the hydrostatic weighing, the first level methods to measure density. In the second part, we'll focus on the same topics, but this time for the oscillation type density meters. So during this event, presentations will be made regarding new guidelines on hydrostatic weighing, oscillation type density meters, density certified reference materials, and good practice for industry. In the end of this project, in the end of this workshop, we are going to have some opportunity to discuss in the roundtable session. So these are some rules that I saw that my colleague already told you. So please mute the microphones. You will have the opportunity to speak with us in the end of this workshop. In that time, you can turn on your video and, of course, turn on your microphone to make your questions. So to make the questions, raise your hand, and the moderator will speak with you, and you'll have the time to make the question. So firstly, I would like to speak with you about what is the rhoLiq project. So rhoLiq project was or is a €500,000 project of 2070 EMPIR call. Due to the COVID-19 pandemic, its duration was extended from 3 to 4 years. So it's finishing now, in the end of this month. rhoLiq's consortium is formed by 12 European NMIs from Portugal, Austria, Moldova, Czech Republic, Serbia, Poland, Bosnia and Herzegovina, Norway, Germany, Turkey, and Romania, and also one density meters manufacturer, Anton Par. This project counted with the support of several entities, from legal metrology organizations to standardization and also accreditation institutes. Also, the industry supported us, namely from oil, food, and also other density equipment manufacturers. At the level of the European community, the needs and motivation of rhoLiq were: first, to increase the knowledge on the liquid density metrology regarding the effect of the temperature, pressure, surface tension, viscosity, and viscoelasticity. Secondly, to enhance the competitiveness and confidence of the national industries, for example, for oil and prepackaged food, by producing accurate density measurements fulfilling the European directives and national laws. It was also found the need of update the international standards and reference documents using legal metrology regarding the use of the oscillation type density meters. And finally, the need of creation of guidance documents for the meteorological, scientific, and industrial communities. From the point of view of the emerging NMIs, meaning the less experienced ones, rhoLiq came to fulfill the need of implement or improve liquid density measurement capabilities at first and second levels. To demonstrate competence and comparability of these measurement results, to provide new measurements, calibration service and CRMs to accredited laboratories, research centers, and industries. rhoLiq counted with three major objectives. The first one was to implement the national measurement capabilities in liquid density metrology in less experienced NMIs, as I already said, in the hydrostatic level, within a wide density and temperature intervals within this uncertainty interval, 0.002 to 0.005 kilogram per cubic meter. Also, for the second level, we aim to improve the capabilities with this level of uncertainty, 0.010 to 0.05 kilogram per cubic meter at atmospheric pressure, and also at high pressures up to 600 bar, with an uncertainty 1 magnitude higher than atmospheric pressure. Other objective was study the robustness of these studies, concerning liquids physical properties such as viscosity, surface tension, viscoelasticity, and also temperature and pressure. And also, of course, to implement the knowledge for density CRM's production. The second objective was to establish the degree of equivalence of density measurement via comparisons with the purpose of CMC publication in the QCDB of BAPM. The last objective was to empower the less experienced NMIs with the knowledge and tools to develop their individual strategies for long-term operation of the developed capabilities. To achieve these objectives, a work plan was set comprising 5 work packages, 3 of them technical ones. The first one, the work package 1, was involved training and strategy development. Work package 2 related with the activities of the hydrostatic weighing, and with the work package 3 related with the oscillation type densitimeters. So in terms of impact, this project aimed to impact through the elaboration of draft versions of 3 Euromed guides, one for oscillation densitimeters, hydrostatic weighing, and also for reference materials for density, to be revised and hopefully approved by Euromed TCM. A good practice guide for industry, and also to give input for the revision of a series of reference documents from ISO, OML, WELMEC, and by providing moments of training like this one to disseminate best practice in metrology, in this metrological area. So you can find this and more information about the findings of this project at rhoLiq's official website, or you may stay longer with us and assist to this workshop. So thank you so much once again for joining us. We'll have the next speaker, Dr. João Alves e Souza, that is the head of Portuguese National Meteorology Institute. It's going to give a brief presentation of IPQ activities on research. So please, Dr. João, the floor is yours.
Thank you very much. Let me try to share my screen. Okay. Can you see it?
Yes.
Okay. Okay.
Yes, go ahead.
Right. Okay. So, first of all, a word of appreciation. Good morning to you all. First of all, a word of appreciation to to all of you, and in particular to the coordinator, Andrea. You that have worked so hard to see this project through successfully. I think it is a very important topic, relevant among other things in international trade. Whenever you have a product that is labeled, for example, in volume and has to be verified by weighing, for example, and being measurements in density, not always very well understood, the importance of the research topic, I think, is demonstrated. It is a pleasure to host both the final meeting of the project and this workshop, and I hope it will be technically fulfilling. You'll have fruitful discussions that will lead to a knowledge transfer and make it worthwhile. I will now give you a brief overview of IPQ and our national laboratory and some of our activities. Okay, so now, right. So we have this the metrology department, of course. We are the National Measurement Institute, but we are also the national measurement, the national standardization body. These are the two operational departments, and then we have some supporting units that deal with international affairs and administration and so on. Right, in terms of the National Metrology Institute, you can see here that our unit, the National Metrology Laboratory, the core activity is scientific and applied metrology, and then there is legal metrology in another unit. We have signed the meter convention from the beginning, and we also signed the mutual recognition arrangement. And for that, of course, we need to have a quality management system implemented and to participate in interlaboratory comparison in order to have our CMCs in the BIPM database. Right, so in this slide here, you can see the three main our activities split in these three vectors, and they are equally important. It makes no sense being without any of them. We have the applied metrology, which is our mission to give support to the network of accredited laboratories in Portugal. But of course, we need the scientific metrology to evolve and keep up with technological development, and that's what distinguishes us from other national laboratories. And of course, all that is underpinned by the quality management system that guarantees competencies, since we are evaluated every year by peers. So this gives you an idea of the structure of the metrology laboratory. In IPQ in total, I think we are 117 people, of which 42 at the metrology department, and this number here for the National Metrology Laboratory is, I think, outdated. We are 24 now. We have more people than any other department. For example, the standardization department, I think they are about 22, but still we are too few for the amount of work that we do. We have a lot of multitasking, as you can see here. For example, the mathematical and computational group, we are 5. In quality group, we are 5, but it's not 5 people that only do that work. We are all the same that work in the technical activities, and also in these activities of quality, mathematical, bureaucratic activities as well. I think we do a very good job in managing that. This is just a few numbers of the National Metrology Laboratory, 3,500 in services in total, including calibration, metrological verification, certification of reference materials, and so on. The turnover, and this is of course to do in a big part to the legal metrology, is 4.2 million euros. We have 142 CMCs and 18 matrices in the key comparison database of the BIPM. Publications last year, 51 in conferences and peer review journals. Organization of events, only 3, but as you know, the last 2 years were a bit special due to the COVID-19. And participation of a research and development project, 12 that are ongoing at this moment. This is another view of our activity. Calibrations among those services are about 2,500. All the representation at the international level, interlaboratory comparison, technical groups, and so on, CMCs again. And in terms of projects, I will give you just a brief overview in what sort of projects and areas we are involved in order to foster a knowledge transfer of technical scientific knowledge and participate in innovation, which is so important for us. So here, these are the projects which includes the rhoLiq that will finish this year. Due to the pandemic, they were extended for an extra 12 months. It's this one and the first one to do with quantum standards in electrical metrology, DIG AC, the digital traceability chain for AC voltage and current, to finish now as well. And this establishing traceability of liquid density measurements. The colors is the green is the fundamental metrology, and the ones in this light brown, let's say, are more to do with industry. And we also have this one, which is horizontal in uncertainty evaluation. Then to be concluded, we hope this year. We have several ones. We have a lot of activity in the health sector. So this methodology for drug delivery is coordinated also by IPQ. Another one to do with health related to the blood pressure measurements. We have another one in industry to do with the dimensional metrology. And the Kelvin one in the fundamental metrology, plus again this one to do with the measurement uncertainty evaluation, and this light blue one here, those are the ones related to energy and environment. So this one is to do with LED lamps, and again started in 2021. Again, quantum standards, in this case for nanometrology. Another one in health, microfluidic devices, seawater, pH and temperature measurements in fundamental metrology, and clean energy in energy. We We are involved in 5 of the European metrology networks: climate and ocean observation, energy gases, advanced manufacturing, quantum technologies, and clean energy. Okay, and the idea is to cooperate with the stakeholders in all these domains to foster research and development, calibration services, integration with the quality infrastructure, and capacity building in knowledge transfer. Okay, these ones will start this year. Another 2 related to environment: metrology support for carbon capture, utilization, and storage, and metrology traceability of measurement data from nano to small microplastics for a green environment and food safety. Okay, these are some pictures of our laboratories, including we have all the base units and many of the derived ones. In this case, mass, dimensional, property of liquids, time and frequency, force, volume and flow, temperature, electricity, photometry, and referent gases. Okay, and just this reflects what I said in a SWOT analysis. Our strong points is that we have excellence in international recognition, and we do the integration of scientific, applied, and legal metrology. We are self-sustainable in terms of revenue, and we have the opportunity to be integrated in European network, the EMPIR and now the EPM, capability for research and development, and the ongoing cooperation with universities and R&D laboratories. And the weak points and threats are related to the fact that we are a public research institute, which means that it's very hard. We don't have much freedom in terms of recruiting new staff, and that is one of the main constraints. And also, it's not easy to buy new equipment. I mean, the budget is limited because we are self-sustainable, but what comes from our activity goes directly into the treasure, and it's not so easy then to use it. Thank you very much. That is all from my side. So let me...
Thank you so much, Dr. João. Hello to all and welcome back. We are now in our second part of this workshop, and we are now going to have some presentations about secondary density measurement methods, the oscillation type density meters. We are going to start with the first one made by our colleague Elizabeth Leonard from GUM, Poland. So please, Elizabeth, the floor is yours. Take your time to share your presentation, and you can proceed.
I will try to share my screen. I see you. Jesus. Can you see it now?
Not yet.
I'm pushing the arrow. Okay. Udostępnij zawartość. I succeeded yesterday. I don't know why I can't do this now. Okay.
Perfect.
Okay, I can? Yes, do you see?
Yeah.
Okay, it's nice. So, hello everybody. I may speak now?
Yes, of course.
Yes. So, I'm Elżbieta Leonard from Poland, Warsaw, from Central Office of Measures, from Department of Physical Chemistry now. And I'm going to tell several words about the draft Euromed guide for oscillation type density meters. And the purpose of this guideline, which was prepared by Andrea and colleagues that you can see here, the purpose is to achieve equivalence and mutual recognition of density measurement results by means of oscillation type density meters, and to give a practical guideline on basic physics of the methods, give recommendations for measurement procedures, and give description and hints for an uncertainty budget. This guide was prepared under the scope of the EMPIR project rhoLiq and contains information on theory, measurement, uncertainty, and also tips and tricks for users of the oscillation type density meters all over the world in all branches science of technology, because they are widely spread since over 50 years. I think we use them in our labs. So the presentation will consist of two parts. I will give the general overview of the draft guide, and Ms. Barbara Lacke from Anton Pau will show you the practical side of measurement. And on this screenshot, you can see all the key aspects of measurement, and Barbara will tell you more about them. So what is the contents of draft guide? First part, abbreviations, acronyms, symbols, signs, terms, definitions, very useful part. Then measuring principle, design, mathematical model, sources of error, calibration, handling, theorems, reference liquids, measurements, uncertainty, traceability, quality assurance, and suggestions for improving procedures. This is a draft guide, and a lot of work will be done in the next month. So we have to transfer the density unit from definitions of kilogram and meter. In density, we have primary density standards. We have kilogram silicon spheres, and we use them in our hydrostatic installations. Now many countries have such primary level installations. You can see here a silicon sphere. This is our one. And we measure, like Jürgen described in the first part today, we measure the density of liquid, and then we either produce CRMs or just take the density of liquid and calibrate our density meters. There is a lot of other methods, other instruments to measure density, but I think the density meters in the recent years become very widely used because they are very friendly, quick measurement with the whole software. On the screen, I dare to put the density meters we had in our lab for measurements, or we have as our reference density meters. I'm sorry if I do not put all the types, but these types were approved in Poland. These are the density meters of the highest resolutions. Like you can see Anton Parr, Mettler Toledo, in Kyoto, Rudolph, Vida, and so on. From the reference density meters or by CRMs, we transfer the density unit to laboratory density meters of different resolutions, and the, let's say, last stage, to handheld density meters without thermostatic system, but there is a lot of them. They are also user-friendly, quick measurement at every place. Okay, so I will tell several words about each part of the guide. The measuring principle is the law of harmonic oscillation, the simple equation. We have the U-tube, which is oscillating with resonant frequency. And when we fill it with different fluids of known density, typically we do it with air and with ultra pure water because we have reference data and cleaning methods to have the ultra pure water. So we can write a relation. We can establish a relation and have some constants, which will let us to calculate density related to the frequency of oscillation. Many years ago, it was noticed that the viscosity has a big influence, and more complicated constructions were invented and more complicated algorithms and mathematical relation to determine the viscosity corrected density values. Also, I have a feeling that we still have some problem, especially for low viscosities. The design of the instrument is described in international standard. This is the one which needs some amendments. And we have different system of excitation of the oscillation. It used to be mechanical, magnetic, electric, and it could be constant oscillation or in the latest years, Anton Parr implemented pulsed excitation. We can achieve additional data from the measurement. Evaluation of the oscillation used to be analog, now it's digital. We still have the old one from 80s of the last century, just don't work as a museum. We can establish mathematical model for this measurement. And the measurement principle is based on the change of the natural frequency of a hollow oscillator when filled with different fluids. So for adjustment, we use air and water as a routine work in our lab. But of course, we can use another reference liquids if we have such a need to narrow the range of the measurement. Input quantities that we have to include, for the first, it's the oscillator properties, it's the thermal expansion of the oscillation, isothermal compressibility, pickup and evaluation of the oscillation signal, temperature sensors. We know that there is a lot of temperature sensors now inside. Elasticity, we have to think about aging of the cell and about contamination. We usually use glass cells, but there are also metal cells, so different behavior. From sample properties, the input quantities are the thermal expansion of the sample, isothermal compressibility, pressure, temperature, viscosity, viscoelasticity, air saturation, all the factors that Jürgen already has mentioned today. Okay, the sources of error and calibration. First of all, we have to perform calibration with appropriate reference liquids. This is the essential key to evaluate the measuring behavior of the oscillation type density meter, because we adjust it with, let's say, air and water, but we also, to monitor its behavior, we have to use reference liquids. And to calibrate it, we also use reference liquids we compare the density meter with a reference one. The sources of error are as follows. First, the proper density, reference density. CRMs covering the density interval of work should be used. And of course, reference materials with the similar physical-chemical properties as we measure every day. Second source is viscosity of fluid, oscillation damping, and density overreading results. We can calibrate with viscous reference materials to correct readings. We can also make laboratory corrections comparing with the results from hydrostatic weighing, make own laboratory calibration curve. Next source is temperature. We can calibrate the measuring cell with appropriate sensor to put it inside. I personally prefer to use reference liquids with different cubic expansion coefficient because it's not dangerous for the cell, and all the temperature errors are inside the density. And if we see something strange results, then we can calibrate it with temperature sensor. The cell is made of thin glass and you can easily deteriorate, to break it, just to make some damages to it. Okay, next source of error is pressure. We should use reference liquids of known density pressure dependence for high pressure density meters. And viscoelasticity, its combination of viscous and elastic behavior. And as we could see from the results of our measurements, we must use methods to evaluate the influence of these viscoelastic liquids. They behave differently. Some words about handling and measurement procedures. We have to obey all the safety warnings and conditions, use in proper environment, and obey to all the rules. We deal with many chemicals, with many solvents, organic solvents, and so on. So we have to stick to the manual and all the warnings and precautions. Also, the procedure of sample preparation is important. All this key Barbara will tell you about in the next part of presentation. Sample preparation is important. I think Jürgen also mentioned that we have to have it clean and in proper temperature when putting into the cell and in proper environment, not to get contaminated. Cleaning of the device is very important because we can measure with the clean cell. If there is anything inside, it will disturb the measurement. Also, this is very important when you conduct an adjustment. The cleaning of the cell, you must be sure that the cell is clean, because otherwise you can just disturb the whole adjustment. You have to perform control measurements. And I just take one graph from our lab, one density meter. They come to us, let's say, every 2 years. And just you can see when the density meter is properly used and clean and curve about, you can see that all the calibration curves are very similar after many, many years of usage. When you clean it, adjust it, the characterization remains stable. Okay, coming to our reference density liquids. In general, besides raw and pure water, reference liquids shall be used for testing, control, and calibration of density meters. The certified values of these CRMs should cover the intended working range of density, temperature, and pressure, and they should have similar physical-chemical properties. The density values of the reference liquid shall be determined in a manner traceable to national standards. And this topic is addressed to in a draft Euramed guideline of density CRM prepared within the scope of this rhoLiq project, which will be presented by my colleague Eva. The preparation, selection, and use of reference materials is also described in the international documents. We have standards, we have guides now. to use. During measurement, the manual provided by the producer should be observed. We have a good established manuals nowadays, and we can use them and stick to all the hints that are inside. The quantity and chemical characteristics of the liquid to be analyzed should be considered. You must be sure that when you measure the liquid and you put it into your measuring cell, which costs, let's say, it's the half of the cost of the whole density meter, you have to be sure that you can clean the cell after the measurement with proper solvents. Okay, what about measurement uncertainty? We use the combined uncertainty, which contains the contributions related to resolution, calibration uncertainty, drift, repeatability, reproducibility. Related to temperature, its resolution, the calibration, drift, and hysteresis, to pressure, to sample properties, and maybe some others contributions like viscosity, let's say. Traceability and quality assurance, the key points are periodic calibrations, the intermediate checks with proper liquids or even with water. The routine is that you check before measurements, you check first with air, then with pure water. Then use of CRMs, and of course participation in interlaboratory on national comparisons, or in rhoLiq project, then we have a lot of data to compare to establish our competences. And guide also contains suggestions for improving procedures concerning installations, the ambient condition, the automatization of the process and data recording, to avoiding electrostatic charging if you use white Teflon, warming up, preparation of test liquids, measuring cells, and use of syringes or different ways to supply the sample. So, thank you for your attention. This was a very short overview on the structure of this new guide. I think that you would have opportunity to see it before the issue, and thank you very much for your attention. Thank you.
Thank you so much, Elisabetta. Thank you for your clear presentation. We are now having our other colleague, Barbara, from Mountain that is going to proceed with the presentation. Please, Barbara.
Okay. I will load my presentation. Welcome from my side. My name is Barbara Lacki. I'm the head of the accredited ISO 17025 calibration laboratory from Anton. I'm not from a National Metrology Institute, but my expertise is actually doing density measurements. And for this reason, I would like to talk to you about some tips and tricks and about doing measurements with the oscillation type density meters. And you will find all these details also in the draft for the new Euromet guide for the oscillation type density meters. You can see here, shall I, this maybe, that's better. You can see here on the slide, instead of the picture of a density meter, I've put a picture of a black box in the center. Because for you, a density meter is like a black box. You should always remember the density meter measures temperature and the oscillation period. But all models within this instrument you cannot change. But there are a lot of influencing factors which you can change and which you should always keep in mind. For this reason, I would like to speak not about the instrument, but I would like to speak about the environment and the location of the instrument. I would like to tell you something about the adjustment and the calibration. Very important are also the regular control measurements and density checks. We have, of course, also an influence of the operator on the density results. And then, very important is also the sample preparation, sample filling. At the end, I will come to the measurement and to the cleaning of the device. Let's start with the environment and with the location. First of all, I really recommend to put your density meter in a clean laboratory with ideally with controlled room temperature, ambient pressure and humidity. If it's not controlled, or if these values are not stored automatically, please write down all these values when you do measurements, because this is important to always know these conditions when you're doing the measurements. Additionally, regarding the pressure, when you perform and when you adjust the density meter, you usually use a liquid which is specified under normal pressure. This means, but you're operating on the ambient pressure. This means you are adjusting, or with your adjustment, you tell the instrument it should be normal pressure. But if there is a pressure difference between the day of the measurement and the day of the adjustment, then there might be an influence on your result. What else is important regarding the environmental conditions? If you have high humidity in your lab, you should use a drying cartridge, because you should avoid the condensation in the cell, in the measurement cell. Do not put the instrument near into direct sunlight, or there shouldn't be a heater nearby, and there shouldn't be any ventilation directly above the instrument. Let's come to the adjustment. I've mentioned before, the instrument measures temperature and density, oscillation periods. For this reason, you always have to keep in mind, probably sometimes you need a new temperature adjustment. This cannot be done by you. This has to be done by authorized service personnel. We recommend it especially for brand new instruments, because when an instrument is brand new, the PT100 sensor might drift a little bit at the beginning. Regarding density, it's necessary to adjust the density meter after removing the adapters, or especially after shipping, or when you ship one density meter from Graz. We have completely different air pressure than in your location, probably. When we ship this instrument from Graz to, for instance, Mexico, then you have to adjust the instrument. Very important for the density adjustment is to perform a proper cleaning and a proper drying before you adjust the instrument. Always use a correct humidity and air pressure as for the input values for the adjustment. I recommend to use a calibrated reference instruments in order to enter the humidity and the air pressure. For the water, please always use freshly degassed, pure or ultra-pure water. The quality of the water is very important, and depending on the isotopic composition of the water, you should choose a matching water table. Jürgen Rauch mentioned this morning already about the isotopic composition of water. And in our instruments, at least, we have 2 different water tables, and please choose a matching water table to your water. Let's come to the temperature calibration. Elżbieta already mentioned that it's possible to calibrate, to perform a temperature calibration only with appropriate PRTs, or only with appropriate temperature sensors. This has to be done very carefully and gently, but nevertheless, it's working very well. I personally prefer this way of measuring of calibrating the temperature. Temperature has a big influence on the density, and this, as you've already heard this morning, this depends on the thermal expansion coefficient of the liquid. For instance, you can see here for isooctane, 1 millikelvin, temperature error of 1 millikelvin shows a density difference nearly of 1 in the 6th gram per cubic centimeter. And for this reason, the temperature is very important, a correct temperature measurement. Let's come to the density calibration. Elżbieta has already mentioned that it's very important to use appropriate reference liquids, and the reference liquid should be within the intended working range. Of course, the instruments may drift with time, and for this reason, you perform a calibration in order to validate the density measurements and the adjustments. Yes, perform periodic calibrations and select an appropriate calibration interval for you. Density checks. Density checks should be done regularly. Every morning before you start working, we recommend to start first of all with an air check. Air check means measuring the density of air. And then measure the density of water in order to verify the accuracy of the instrument. For this, use always freshly degassed, pure, ultra-pure water, distilled water. Only water with a good quality should be used for these checks. And at the end of the day, or after each cleaning, please also perform again an air check in order to see if the cleaning was successful. Warming up of the instrument. Please wait. We recommend to wait at least 12 hours or overnight. Wait after you have changed the temperature of the instrument. Or wait after installing new adapters, or wait after temperature calibration. This is very important. And we also recommend do not switch off the instrument. Always keep it running, and then you can rest assured that the instrument is already stabilized and has a good temperature. Let's come to the operator and to the handling. First of all, I have to tell you, I mean, density measurements, it always seems that density measurements are very easy. You have a density meter and you take a syringe, fill the liquid, and that's it. But honestly speaking, I have to tell, it requires practice. It really, you have to practice in order to get that good density measurement results. Always work in the same way. And I've written down here the repeatability conditions in order for the highest, in order to reach high precision. Always do it in the same way, have the same measurement procedure, and work under the same conditions. The operator is quite important also. Now, you've heard already regarding this sample that we have different influences. Depending on the sample characteristics. You have, of course, there are samples with high density and with high densities and lower densities, or high viscous liquids. Viscoelasticity is also very important. It's not so easy to measure these liquids. There is an influence of the thermal expansion coefficient, you've already learned, depending a small temperature error will show already a bigger, depending on the expansion coefficient, you will see different density changes. It's also very important that the samples are homogeneous and stable. They shouldn't include any gases. The gas content is very important to get rid of gas. And hygroscopic liquids are also, you should know your liquids. If a sample is hygroscopic, you have to work fast or to cover the sample. Additionally, you should check, especially for CRMs, the specified uncertainty, the temperature range, storage conditions, expiration, and the handling of the standards. For the sample preparation, there are different ways of preparing the samples. If your sample contains gases, you can steer the sample or make agitation in order to remove carbon dioxide. You can use an ultrasonic bath in order to remove air, or you can boil water, for instance, in order to remove air. For aggressive samples, please always observe the safety regulations before you start with the measurements. Viscous samples, you can heat them up in order to lower the viscosity. And volatile samples should be covered. And if you perform measurements at higher temperatures, always heat up the samples a little bit before you fill these samples into the density meter. According to my experience, the majority of bad density results are due to a bad sample preparation. And also this sample preparation should always be done in the same way. Let's come to the sample filling. The best way of filling a sample would be using an automated filling device, because then the filling is always done in the same way. But if you measure, where's my presentation gone?
Seems it stops sharing or not?
No, it's just somebody just Steuerung anfordern. Just a minute, you will see my presentation again.
Okay, it's coming.
It's coming again? Okay.
Perfect.
The best way of filling would be the usage of an automated filling device. This is good for an optimal repeatability. But if you measure a CRM, then you usually have only a small amount of liquid. And for these liquids, you have to use a syringe. The best way would be to use a syringe to use it with a syringe holder if this is available. You can see here on this picture, there is an instrument with a syringe holder. With a syringe holder, you get rid of the weight of the syringe on the adapters. Always check if you can see. Also, first of all, you fill the syringe and then you check the syringe if there are some bubbles in the syringe. And if you fill in the instrument, check also the U-tube if you can see some bubbles in there. Please use a glass syringe for liquids like dodecane or ethanol or tetrachloroethylene. Because these liquids dissolve lubricants from the syringe, and therefore we recommend to use a glass syringe. In general, the syringe size should always be as small as possible, unless you use a syringe holder. This was the sample filling. Okay. Let's come to the measurement. Do not forget to warm up the instrument and choose an appropriate precision mode or the highest precision mode for accurate measurements. Keep in mind that the measurement temperature also has an influence. If the room temperature is low and your measurement temperatures are high, you have to first of all, you have to heat up the samples a little bit, and the uncertainty is bigger. If you perform measurements under pressure, if you perform density measurements under pressure, there are different requirements. You have to adjust your density meter under pressure by using adequate, well-specified liquids, and this is quite important for measuring under pressure. Always check the environmental conditions. I've mentioned this at the beginning of the presentation. Then perform several measurements and calculate the average of these measurements. After performing the measurements, you have to clean the instrument, and cleaning is very important. Always use adequate cleaning agents. The first cleaning agent should remove the sample, and the second cleaning agent should remove the first cleaning agent and should be volatile. Do not wait too long before cleaning. And if you are not sure how to clean your instrument, do not fill or how to clean a certain liquid, to get rid of a certain liquid, please do not fill this liquid into your density meter. You can try it. You can try it at the beginning with a glass. You take your liquid and then try to use different solvents. And if you do not find an appropriate solvent, do not use this liquid. I once had the experience that I filled, I think it was, a kind of plastic or some. I felt something and I couldn't clean it and everything got stuck in the YouTube. This was not so funny. For this reason, please always choose an appropriate cleaning liquids. You can do then some pumping and making some air bubbles in order to get rid of the liquids, or sometimes it helps to do some soaking just with a lot of waiting time. And after cleaning the instrument, wait long enough for the drying. For some, of course, it depends on the air pump, or depending on the air pump you use, but it's better to wait long enough. Okay, at the end of the day, you finish with an air check, and if the air check is fine, you did a good job. All in all, I really recommend to keep to keep in mind that density measurements, that there are such a lot of influencing factors, but if you know this, you will get brilliant results. That's all from my side. Thank you very much. And yeah.
Thank you so much, Barbara, for your clear and very useful presentation. I'm quite sure that from the audience we are going to receive more than this question that I'm seeing here. So I think now that it's time for Elizabeth again to show us, or to present us the results of our robustness studies on the...
And Andrea, I don't want to be the first because I think you have the general parts, more general parts in your presentation than I have in mine.
Okay, no problem.
Okay, no problem. Okay,
okay.
Thank you.
That's no problem. So I will proceed. It's the same, but I'm going to present now. So let's now take a look into the findings regarding the robustness studies of oscillation density meters regarding viscosity, viscoelasticity, and pressure effects. Okay, so firstly, I will recap about the needs and the impact of this research topic in our society. Then I will take a look in how these questions were addressed, what was the research line, and some of the results will be pointed out. And lastly, I will briefly summarize some of the most important outcomes from this work, namely conclusions, remarks, and future works. Liquids, as any other state of the matter, possess physical properties, namely the mechanical ones, meaning the ones that describe behavior under the action of a load, such as viscosity, frequently pointed out as mechanical equivalent of a dashpot that you can see here. I can move the dashpot. Yeah, sorry. Described by one of Newton's law, and elasticity represented as mechanical equivalent of a spring that you can see here in the other side, of stiffness K under Hooke's law, will depend upon their inner structure, arrangements, and molecular bounds on the force applied, type, magnitude, and direction. And of course, will depend on the evolving conditions such as temperature and pressure. Meaning that in this roadmap, one may go from the right-hand side with an ideally viscous liquid, a Newtonian one, that dissipates all energy by flowing with a certain resistance given by the viscosity, and in the opposite direction, we will have Hookean law, a solid, with immediate response to the stimulus and full recovery. In between, we will find viscoelastic materials that will show both behaviors when under stress. It is quite easy to think of hundreds or thousands of liquid types that are produced, used, or handled in many ways or applications in a daily basis worldwide. But maybe for a common end user, it's not so clear or evident that the impact of the accuracy and precision of the density measurements of these liquids be performed through all these fields, for instance, to control the quantity of a product or its quality, or even to feed data for climate modeling. And besides the great variety of mechanical and other physical properties, liquids are handled and processed in a very wide window of temperatures and pressure. Quite obviously, when the density of these liquids need to be measured, one needs to pay attention to several points. The available methods in terms of cost, time, and volume of sample necessary, and more importantly, from a metrological point of view, the intended measurement result accuracy and uncertainty, meaning that the selected method needs to be assessed for the influence of liquids properties and measuring conditions in order to gain knowledge regarding if the method is fit for the purpose. Just to give you an idea of the hierarchy scheme of dissemination of the density unit for liquids, you can see here this pyramid, and has the densities being defined as the mass of a given volume of substance under fixed physical conditions of temperature and pressure. Density unit is traced back to SI base units, kilogram and meter, by means of the use of a solid density standard of traceable mass and length in hydrostatic weighing method. But this research was focused in a 50-year-old working standard, intensively used in industry and also in some research laboratories. The oscillation type densimeters. So, as already was mentioned by Elisabetta, the measuring principle of an oscillation type densimeter is based on the law of harmonic motion of a flexural oscillator, constituted by a hollow tube, the oscillator, that change its natural frequency when it's filled with a fluid. In short, this oscillator is subjected to an oscillation force mechanically or electrically by an excitation transmitter, and the resultant oscillation is evaluated by optical pickup that determines the period of oscillation. To understand this measuring principle, we need first to recall some of the mechanics theory regarding the physics of a simple harmonic motion of a system composed by a mass, m0, on a spring of stiffness k, displaced from its equilibrium from a position x0 by an external force subjected to a linear elastic restoring force proportional to a sinusoidal displacement. This system will oscillate with a natural frequency omega 0, determined solely by its mass m and by the spring's stiffness k. Considering now the real case where we insert a fluid of density rho inside the oscillator, resulting in an increase of system mass of rho times the inner volume of the oscillator, leading now to a lower resonance frequency. Samples density can therefore be deduced from the measurement of periods of oscillation, tau. Most of these instruments use as working equation a second-order empirical relation between density and the squared vibration period, represented by the equation below, where A and B coefficients are physically meaningful parameters of the oscillator determined by the calibration fluids by using at least two fluids. However, different types of mathematical models can be used. Now we'll replace the first liquid with one with viscosity eta. Besides the change on the total mass of the system, the viscous liquid will act like a damper, causing a viscous drag, exerting a frictional force in the opposite direction to the motion and proportional to the velocity v and to the viscous damping coefficient c. This frictional force is the result of two effects. First, the formation of a fluid boundary layer of thickness delta in the inner wall of area A and length L of the resonator, leading to an increase of its inertial mass. And secondly, the damping of the oscillation is due to the wall shear stress acting on the resonator. In this case, the resonance frequency of the system is now affected by a damping ratio eta, where gamma is the damping ratio, a dimensionless measure that describes how oscillation in the system decay after a disturbance, whose value is given by the ratio of viscous damping coefficient by the twice of the system mass, and C, the viscous damping coefficient that is directly proportional to the viscosity and to the inner area of the oscillator, and inversely proportional to the boundary layer thickness. Now that we already recall some of the theory, let's take a look into the developed work under this topic. The research was undergone in two main groups. The first one with the objective of performing a metrological assessment of these instruments, meaning to study the influence of liquids properties such as viscosity in Newtonian liquids and viscoelasticity in non-Newtonian liquids, and also the influence of pressure. Let's now look in the first group, how viscosity affects the density measurements. So, as already mentioned, fluid viscosity will produce two parasitic effects in the oscillation. On one hand, the shear forces generated between the fluid and the tube wall, and on the other hand, the formation of a fluid boundary layer will increase the inertial mass of the oscillation system. These two effects will lead to an oscillation damping and therefore to density over reading results. Thus, this part of the work consists in a set of investigations on the effect of samples viscosity, and it was performed by the 12 partners of the rhoLiq project, and with a total of 15 borosilicate made oscillators, commercial ones. So, although most oscillation densimeters possess mechanisms and algorithms to correct viscosity caused damping, they are still found insufficient to obtain accurate density values able to fit the purpose of their use. So, the main goals of this investigation was to produce a reference damping curve. And we were able to study this influence in the very wide viscosity range from 0.6 to 7,750 millipascal second in the wide temperature interval from 5 to 16 degrees Celsius. From the total of 269 generated data, only half of them found to be satisfactory. As can be seen in the chart representing the mean density deviation values against samples dynamic viscosity, the major dispersion happens for low viscosity values. However, to be taken into consideration is that for these low viscosity values, the samples under test were water-based, and therefore other phenomena can be causing this scattering, like gas content and other things that Barbara already told us, and Jürgen as well. On other hand, this wide viscosity range was only possible to obtain by changing the temperature, and that means that lower viscosities are related with higher temperatures. So this dispersion may also be related with deviation due to temperature errors. Now let us consider only the deviations of the satisfactory results. As can be seen in this figure, it appears to be no dependence on the density deviation and sample's viscosity value. Interesting to be noticed is that the maximum mean deviation, the maximum mean deviation value was minus 0.048 kilograms per cubic meter with an expanded uncertainty of 0.042 kilograms per cubic meter, for the nominal dynamic viscosity of 0.8 millipascal second, and the second one for the dynamic viscosity of around 18 millipascal second. You can see it's in the here. Also to be noticed that beside these 2 points, the mean density deviation was 0.0004 kilograms per cubic meter with the mean expanded uncertainty of 0.021. You can see in the green lines. From this, one can conclude that the partners were able to overcome the viscosity damping with their calibration curves. For these reasons, it was not possible to conclude about the viscosity influence in density errors, as the density results were already corrected for these effects. So as you may know, these instruments can provide 2 types of density indications, one without viscous damping correction and the other one with the corrected for this effect. So when these devices are not considering samples viscosity induced effects on the oscillation, the increase of the inertial mass of the oscillatory system and the effect of energy dissipation as frictional heating between liquid layers in the boundary layer will lead to a dampened resonance frequency lower than the oscillator natural frequency, as the frequency is only considered to be dependent upon the spring stiffness and the mass of the system, meaning that without viscosity correction, the density meter will overestimate the mass of the liquid, leading to a positive deviation in density results, as we may observe in this curve. In previous unpublished investigations on Newton liquids, it was seen also a linear dependence on density deviations on the square root of dynamic viscosity, up to approximately 300 millipascal second, reaching then a plateau of maximum density deviation when the thickness of the fluid boundary layer was equal to the inner diameter of the oscillator cell. Here, the density deviations does not longer depend on the square root of the dynamic viscosity. Interestingly, this figure shows a very similar linear dependence of density deviations on the square root of dynamic viscosity, but now up to around 365 millipascal second, reaching then a plateau of a maximum density deviation value around 0.620 kilograms per cubic meter. I just want to remind you, this is the average mean of the satisfactory results obtained by all the partners with different density meters. So take this into consideration. And of course, this is something that will depend on the oscillator. This is not can be used as a rule for all oscillators. Just to prove that the mathematical model is useful here. So I will just give this information. I will leave it in the presentation. I will not be go deep in this because this is the explanation behind the boundary layers theory. If you want to know in more detail, I can just send you the presentation. We have it everything here, and you can see here why is coming this this relation between the density deviation and the square root of the dynamic viscosity. This is just for you to have the equation where this is coming from. So looking now to this figure representing the relative density errors of density indications now corrected for the viscous damping against the square root of viscosity, it can be seen that no trend was found in these results, and the mean density deviation of density indication with viscosity correction is around 0.011 kilograms per cubic meter. So very good results indeed. It can be said that, in average, the inertial mechanisms used by the density meters were able to reduce significantly, the deviations. To obtain, of course, more accurate results, it is clear that one should select the most appropriate curve to obtain to be used afterwards. But the results were quite surprising. So now from Newtonian samples to non-Newtonian ones. So this time the oscillator is going to be filled with the viscoelastic sample that, for a matter of simplification, we are going to consider this, that is mechanical behavior under stress is described by Maxwell model, the spring and dashpot. Whereas a spring element representing the elastic behavior, as I already told you, and the dashpot element are in series, like this representation here. The effect of samples viscosity in the oscillation was already described, and the effect of samples elasticity will lead to an increase of system stiffness by adding a delta K. So viscosity is lowering the oscillation, elasticity is enhancing the oscillation. In order to provide a deeper insight into the damping effects produced by this kind of liquids, we prepared two samples of two different non-Newtonian liquids. Their mechanical properties were investigated resorting to a rheometer and by oscillatory tests. And in this activity, 5 partners take part, and 8 oscillators were used. The results of this study showed the possibility of determining density of viscoelastic samples by means of hydrostatic weighing. I have here both the results from hydrostatic and also from oscillation density meters, just to compare because we use as reference the hydrostatic weighing because they are not, or supposedly not, so affected by the viscoelasticity of the samples. It was seen that the density weight mean values obtained by hydrostatic weighing and oscillation density meters for both samples were not metrological compatible, meaning that the effect of samples viscoelasticity in the oscillation density meters are still not adequately corrected by the partners. Therefore, further work should be done by each participant to check the sources of uncertainty and errors that have not been fully assessed in this comparison. As described, the mechanical properties of NNLs were determined by oscillatory tests by means of a rheometer with the purpose of determining their dynamic viscosity and storage viscosity. So the first one related with the viscosity itself and storage viscosity related with elasticity. At 2 moments, one at rest and the second one with the samples under the oscillation frequency produced by the density meters while they are measuring. At rest, it was seen that at rest, both samples presented a liquid-like behavior with predominant viscous behavior. Under the high frequencies generated by the oscillator, both samples presented a solid-like behavior, with a storage viscosity value around 9-fold and around 4-fold the dynamic viscosity value. The results of the viscosity tests with the Newtonian liquids show a linear dependence of viscosity deviations on the square root, as I already said, up to a maximum value of viscosity and then reach a plateau. However, both samples, viscoelastic samples, show values of dynamic viscosity much higher than that maximum value of dynamic viscosity, meaning that the mentioned plateau was already reached, and therefore a maximum deviation of minus 0.62 was expected to be used for density indications. But it was not the case. But as can be seen, the first value overestimated by far the necessary correction to be applied to the viscoelastic density values, and the second value underestimated it. Thus, it seems that the elastic part of the liquids is attenuating the viscous damping, and therefore the corrections cannot be used. The corrections that are used for Newtonian cannot be used for non-Newtonian liquids. Let us now focus on pressure-induced errors. So several applications nowadays demand an improvement of the knowledge and of pressure-induced errors. For this, it's also necessary to develop and validate a reference method traceable to SI units. So the pressure-induced errors are mainly related to the fluid and oscillator compressibilities, being the first one the most significant. And in the simpler way, an increase in pressure will lead to a lower resonance frequency. Unfortunately, we didn't have the time to do these investigations under the scope or under the scope of rhoLiq project, but in Europe, at least we have 2 high-pressure liquid density measuring apparatus that are based on oscillation density meters and are able to determine the fluid's density up to 650 bars. And I will just show some schematics of one developed at PTB and one at IPQ. So both apparatus were homemade, assembling composed by several parts, as we can see here in the scheme, being of the importance the oscillator, a commercial density meter, the pressure generator, in this case a piston pump, and the pressure monitor. The other parts are high pressure tubing and valves. Here you can see the case of IPQ apparatus. The big difference here lies in the pressure generator, which is in this case is a high pressure pump. Some advantages of using this type of pump were found, such as smaller volume of sample needed and the easiness of cleaning. So the developed apparatus were calibrated using ultra-pure water as reference using the CIPM formula. And also we validate the density measurements by using another liquid no-name against the reference values. Also, because the intent of this apparatus were to be used as a PVT system, it was necessary to calibrate or determine the internal volume. So we did it by gravimetric method using dodecane, because water is very difficult to handle. And by doing this, we are able now to produce density measurements traceable to SI units of mass and volume. In the very short conclusion, we were able to produce to produce density measurements with a mean uncertainty of 0.35 kilograms per cubic meter. So, in terms of general conclusions, regarding the viscosity-induced errors, we see a linear dependence on the square root of the dynamic viscosity, and then ending in the plateau when the thickness of the boundary layer is reached. And then regarding viscosity-induced errors, was not possible to establish a causal relation between sample viscosity and density deviation. We saw that also the calibration curve obtained with the Newtonian Oz are not useful to correct the density deviation with viscoelastic liquids, as the elastic portion seems to attenuate the viscous damping. And regarding the pressure-induced errors, unfortunately, we didn't have the time to produce more results about this, but at least we have schematics of two different apparatus for a high pressure, and we need to, of course, to make further work to reach a wider temperature range and also to decrease the uncertainty obtained. So from my side, that's it. I hope that it's going to be useful. Thank you. Hi, Elspeth, do you want to present your part now? You are muted, Elspeth.
I'm muted, yes, but
yes, okay.
I see on my screen that it should be shared. It's not. Okay, I will do it once more.
We are seeing. You see? No. Yes, again, we are seeing it.
It's on the screen. Yes,
yes, yes, it is.
Okay, I'm happy.
So go ahead.
Okay, so I will tell a few words about the effects of temperature on the rhoLiq project. There was a great amount of data gathered in the last weeks. So here are the first conclusions after the analysis. We have, in this task, we wanted to study the robustness of density meters concerning the influence of viscosity and temperature. And we decided to merge these two activities into one, robustness regarding viscosity and temperature. This created the opportunity of analyzing a wider range of viscosity. And the liquid samples were measured at 5 different temperatures at 5, 10, 20, 40, and 60 degrees Celsius. The technical protocol was prepared in November last year by BVPTB GUM, and we included all recommendations by Anton Parr. So density of samples used in the comparisons, and 2 high viscosity oils were used. It was water, deuterized water, dodecan, tetrachloroethylene, and 3 oils, 1 if 160A, 1000B, 2000A, all the samples were prepared and distributed to partners by PTB. The measurements were carried out at atmospheric pressure. The reference density values were determined at the comparisons and by PTB and BV. Viscosity values were determined by PTB and also by GUM and by IPQ with Tabinger viscometers and with below the capillary viscometers. So, what were the instruments we used? As you can see, all the instruments were by Anton Parr of different types. From the older ones, as you can see, our is over 20 years old, and in the last month we purchased the newest one and we use it in comparison. You can see as far as I hope all are included, all density meters. Measurement generated for viscosity and for temperature 268 data, and Andrea already said that half was with satisfactory results, and two approaches were used to determine the degree of equivalence of density results. And the first approach was the reference value taken from the hydrostatic method. You can see the table with reference values, and for temperature I use only these reference values. So the second approach was the weighted mean taken into account. I will skip the equations because you know all these equations. As I said, we used the 7 liquids, and samples we used were delivered, partially they were delivered in 10 milliliter ampoules. The oils were delivered for density meters in 250 milliliter bottles, and some samples were also used from big bottles, 1 liter bottles from hydrostatic weighing. And here is the representation of the all results. Dependence of temperature, you see big scattering, and only half of the results were satisfactory. But the general conclusion was there is no dependence of the density deviation in temperature, because the results were consistent and it looks like the partners were able to overcome the temperature effects in the density results. And then I tried to separate the fluids according to their temperature cubic thermal expansion coefficient. And you can see the results. Here are all results, not only half of results, but all the results of measurements we have made all. So for dodecane changed a little its density during these 2 years. So you can see for dodecane, for water, which should be very good because we adjust the instruments by means of water. Here you can see for tetrachloroethylene, which has the big cubic thermal expansion, value 1.6. So we see the deviation. They are a little bit higher, but nevertheless, the results are quite good. And I will see you first the next slide, because we have viscous oils with high viscosity, and you can see the results for these viscous oils are quite good for oils. They are referred to values from hydrostatic weighing, and they are consistent within the whole temperature range. And coming back to this oil of lower viscosity, you can see the big scattering. It means that this is the very sensitive region of viscosity for density meters. So I have some issues to consider. So the first, in summary, all the partners use density meters produced by Anton Parr. Although there were several generations of these density meters, the last one with different method of measurement. And for this DMA, the air-water wide range adjustment performs a sequence of water adjustments followed by air adjustment at the temperature 60, 40, and 20. But there is no adjustment for lower temperatures, at which additional effects may occur, both for oscillation type density meters and for hydrostatic weighing, mainly I mean humidity. And the big difference of temperature inside the cell and in the environment may also matter, may also influence the results. Only 52% of total generated data revealed to obtain satisfactory results against the reference value. And to assess this outcome, some additional aspects influencing the results should be analyzed. And I try to divide the results because viscosity corrections, especially in this low region of viscosity, could affect the temperature robustness results. Additionally, the issues we talked about yesterday, that we noticed density differences between liquids in bottles in ampoules. So we should also analyze which results were taken for bottles, which for ampoules. For tetrachloroethylene, there were 0.05. For oil, even up to 0.1 kilogram per cubic meter. And next, some issues. And due to unpredictable circumstances, I mean COVID and pandemic, 2 years elapsed between the delivery of the ampoules and measurements. And it seems that when they are preserved in the same condition, it should behave in the similar way, but you never know this. So there was the time result, the time effect on the results of our measurements. And my reflection was that the most certified reference materials, from my experience, needed by the users of density meters are in the range from 15 to 25, sometimes for higher temperature. And beneath 15 degrees, in our lab, we calibrate only the densimeters with low resolution. So our results, I think, can approve our technical competence to do this. Okay, and the last conclusion is that the amount of data generated in this task of the robustness of oscillation type density meters provides a basis for the further analysis, and we should work sometime more to assess all the results. So this is all for temperature. The main conclusion was that we can deal well with this parameter, with these instruments we have, and I thank you all for your attention. Thank you.
Thank you so much, Elizabeth. Yeah, you are right. We need perhaps 1 more year just to analyze all the data and to
exactly
and to have some conclusions. Yeah, but in the end, it was quite good to see that most of the partners are able to handling these temperature-induced errors. So we are ahead of time again. That is very good. So we have time for a coffee break or a tea break or whatever you want to do. So we'll be back again 3:30 Portuguese time. Please be back, and we'll have a presentation of the new guides for the reference materials, also the good practice guides for the industry, and then we'll finish the workshop with the round table, and you can make your questions there. So see you soon. Hi again, we are back. I hope that you have a nice time to to grab and drink a coffee or a tea. So it's now time to present the other two guides. It's time for Eva from GOM, Poland, to present the new guides for production and certification of reference materials for density. So please, Eva, the floor is yours.
Thank you, Andrea. I will share my presentation.
Yeah.
Can you see it?
Yeah, perfect.
Great. Good afternoon, everybody. My presentation is about new guide for production and certification of reference materials for density. This guide was prepared under the scope of EMPIR project, rhoLiq. It will be published as Euramed guide. At this point, sorry, I have, okay. At this point, the first draft of the guide has been written. It has been produced to provide a useful practical guideline on the production and use of liquid density reference materials by hydrostatic weighing and by oscillation type density meters. The guide describes the key steps for production of liquid density reference materials, including characterization, certification, the methodology for homogeneity and stability assessment and uncertainty assessment. There is also some useful advice for candidate liquids to be used as liquid density reference materials. And there's also some useful information about metrological traceability, about certificate preparation, about packaging, labeling, storage, transportation, and stability monitoring. The guide is written in accordance with the ISO standard 17034, which outlines the general requirements to be met by reference material producers to demonstrate competence. The guide is also consistent with other international documents, in particular with the ISO Guide 35, which provides detailed guidance on homogeneity and stability assessment and characterization of reference materials. The guide provides also advice on selecting candidate liquids for density reference materials. After selecting a material, it is usually prepared as a batch of unit. So the material is divided and distributed from a container into individual units, for example, bottles or ampoules or vials, white or amber. The selecting of appropriate packaging is very important because it might affect the stability of the reference material. So in the guide, there are also some tips for packaging and for labeling, because each unit should be labeled appropriately. In such a batch of material, it is important that all units are the same within the stated uncertainty. And it is also important that the material within each unit is uniform. The reference material should also be sufficiently stable for the intended use, so that the end user can rely on the assigned value at any point within the period of validity of a certificate. There are two types of homogeneity and two types of stability relevant in the production of reference materials. The between unit homogeneity is important to ensure that each unit carries the same value of density. Within unit homogeneity is important where several samples can be taken from one unit. Long-term stability, which is important to ensure that reference material is stable under long-term storage conditions, and short-term stability, which is important to ensure the stability under storage conditions. The next step is characterization of the reference material. Characterization refers to the determination of density value and uncertainty arising from this determination, UICAR on the slide. The uncertainty evaluation is particularly important for certified reference materials because it is required for them. By combining the results from homogeneity and stability studies with the results from characterization studies, the value of density is assigned to the batch of reference material, and furthermore, combination of the uncertainty components from characterization, homogeneity, and stability studies provides the evaluation of uncertainty of certified value, UCRM. The density value of the reference material might be determined by hydrostatic weighing method, by oscillation type density meter, or by other adequate method. The methods of determining the density value with the accompanying uncertainty are described in two other guides written under the scope of this rhoLiq project. The previous presentations were about them. For homogeneity and stability study, several subsamples are from the batch are taken for measurements. In the stability study, the differences between units are related to the different exposure time of to storage or transport conditions. For homogeneity study, there are several possibilities to conduct the measurements and analyze the results. When there is no need to within unit homogeneity study, one-way analysis of variance can be used for estimating the uncertainty associated with between unit homogeneity. But when all measurements cannot be made during one day, then the drift of measuring instrument can be one of the source of variation, and then two-way nested analysis of variance can be used for estimating the uncertainty associated with homogeneity, between unit homogeneity. When material from one unit can be divided into smaller samples, then the within unit homogeneity should also be assessed. In the case when all measurements for all samples and for all units are made under repeatability conditions. So in one day by one operator with the use of one measuring instrument and so on, then the measurement results are differentiated due to two factors, within unit and between unit heterogeneity. In this case, two-way nested analysis of variance can be used for within and between unit homogeneity analysis. On the slide, you can see the table of two-way nested analysis of variance. Both the between unit and within unit homogeneity components, UBB and UWB, can be computed using parameters from this table. And this case is described in detail in the guide because it is convenient to conduct measurements in this way with an oscillation type density meter. For stability study, the objective is to test for any important change over time in storage or in transport. A simple linear regression might be used to determine if there is a tendency in a batch of material to unidirectional, so increasing or decreasing change in the density value over the life of the batch. A linear model is fitted to the data and the regression parameters are computed, the slope B1 and the standard error of the estimated slope SB1. These two parameters are needed for further analysis. The uncertainty due to long-term stability associated with the predicted change is given by equation on the slide. Here SB1 is the parameter computed from the regression. And for short-term stability study, the objective is to examine the effect of expected transport condition or several conditions that might occur during transport, for example, extreme temperature. So the units are exposed to the tested condition, and after the exposure time, different for each unit, the material is measured. And then the statistical significance of any trend found is checked. The test for instability is student t-test for slope significantly different from 0. Here the t-statistic is computed from regression parameters, the slope divided by its error. If the value of t-statistic is out of the rejection area, it means that the statistically significant trend is not observed and the material is stable during transport. And by using this test, it might be confirmed that the effects of transport do not significantly affect the density value and do not require an increase in the uncertainty for density value. So the uncertainty associated with the short-term stability is usually omitted in the uncertainty budget in this way. And the next step is preparation of a certificate or other document for not certified reference materials. This document contains the information about density value, about accompanying uncertainty, and some more information such as validity period, use, storage, metrological traceability. Apart from that, the reference material should be stored and transported under appropriate conditions, and these conditions should be specified. The stability should be also monitored for the whole life of the batch of material, and all these important issues are described in the guide. And that's all from my side. Thank you very much.
Thank you so much, Eva. Yeah, you make it sound easy. Thank you so much for your presentation. Now it's time for Pekka from Norway to present a new guide for good practice. So Pekka, the floor is yours. Go ahead.
Thank you. So, thank you, and thank you for all for staying with us for so long, especially for those whose estimate in the middle of the night or something like that. My name is Pekka Neuvonen, and I'm from Justerivesenet. I'm one of the less experienced members in this at the beginning, at least of this project. And then I have been editing and gathering the information for the good practice guide for the measurement of the density of liquids in industry. All of this information basically is already said in this during this workshop. So I won't be going through in details the theories and everything again. So I will be just telling the content and the structure of the guide. The guide is not, it doesn't have the same standard as the technical guides, Euromed technical guides. It's only produced in this project for a general purpose. And we will try to get it out on the public as soon as possible, hopefully within a couple of weeks. It will be published on our website and probably also on different institutes' websites and wherever we find place to put it out. So this good practice guide, it's part of this rhoLiq project. It's the activity 415. It builds on several different activities in the projects where we have been gathering information about the oscillation type density meters and the use of those instruments. And it's a collaboration with all the project partners, and it's basis heavily on the technical guide and then some tips and tricks included. So as mentioned, so it focuses, or it talks exclusively about the oscillation type density meters. We try to focus a bit more on the industrial needs and try to cut down a bit of the theory, so it would be easier to read and easier to implement. It's not a scientific or technical guide, but it serves also as an kind of a starting point if you want to dive deeper into the theory behind. So the first part is the oscillation type density meter basics and basic principle behind it. We start out with the oscillating system. We add some mass and volume and how these affect on the frequency. And we end up with the general equation for the density. And pretty much all the equations are on this slide, so it really doesn't go that deep. The idea is that then when we publish the technical guideline, Euromed technical guideline, so people who has the need can find it from there. Then we go to the sample preparation. It's one of the most important parts of the measurements, as we heard from several persons today. So we focus a bit more on that part. One of the important messages what we want to get through is that you need to know the sample which you are measuring. That is for health and safety reasons, which we don't discuss in this guide. But it's also for that you can guarantee that the materials you are using, like the syringes and everything, that they are made of materials which actually can tolerate or can handle the sample, so they won't break during the measurements. Then, of course, as mentioned before, so how to clean the sample. So you should always test it some other kind of, not put it in straight into the system, test it somewhere else that you actually can remove it. And then, of course, how you dispose the sample, and can it be mixed, for example, with the cleaning agents or cleaning agent, the second cleaning agent, for example. Then we discuss the choice of syringes. For example, how does the size of the syringe affect the measurements? Which size, which type syringe you should choose, which type of material, and so on. Also, it's very important for some samples to be degassed before you start measuring them. So we go through some of the methods for degassing and some warnings what you shouldn't do with some samples. We also discuss a little bit of the samples with high viscosity. How can you get it into the syringes and into the measurement device? Then we discuss instrument preparation, mainly things like environmental conditions, as Barbara already said earlier or discussed earlier. So choosing the location for the device that it's not subject to like air conditioning or direct sunlight, direct heating, and this sort of a thing. Also, then during the use, that you should that how, for example, dust would impact your measurements, and why is it important to that the environment is also clean. And then generally the measurements of the environmental conditions while you are measuring. Then part of the instrument preparation is also to make sure that your device is actually measuring and functioning properly. So we go through the control measurements. We recommend to do a daily air and water check, at least if you don't measure daily, so at least before, at the start of the day, you are starting to do measurements, so check the instrument. And only in the case that the checks fail, so you should do the adjustment. But all this is described in detail in the guide. Then comes the measurements. We give only a very simplified measurement procedure, more like good practices. Because every laboratory has a bit of different needs and different facilities and how they want to operate things. So every laboratory should be writing their own routines instead of just copy-paste the general guide. Then we discuss, the sample injection. Barbara also mentioned that it's very important for the repeatability, that the injection always happens the same way, and you try to do it as the same way as possible. Also connected to the injection, it's the bubbles which can form with some liquids when you inject, and also after injection when you let the sample stabilize. How to deal with these things, we give a short overview. Then we discuss the temperature stabilization. You should let the sample stabilize, and then the measurement cell, the whole measurement cell and system to stabilize to the wanted temperature before you start the measurement, to ensure the highest accuracy. Then we mention very shortly non-Newtonian liquids or viscoelastic samples. And that's also without diving more into the theory behind it, but we just give our recommendation. After the measurements are done, so then you need to clean the instrument. So as mentioned before, again, so you should know the sample. So you should have already chosen the cleaning agents. What do you use as a cleaning agent 1? what do you use as a cleaning agent too. As suggested, we recommend usually 2 cleaning agents. We give a very simple cleaning procedure and also a general guidelines for choosing the right, or where you can start the search for the correct cleaning agents. And then we give a small little advice on specific cases. For example, what to do if the sample has the proteins which coagulates to the walls of the measurement cell, and how to get rid of it, and some things again what you shouldn't do. Then we go to the results. So in general, the display reading is not the accurate result. So we go through the which corrections you should be applying if accuracy is needed. So we talk about temperature and pressure and viscosity. And then, of course, any measurement which is done, it is not traceable without the reporting the associated uncertainty. So therefore, we give a short and general description of the uncertainty. What is it in general? We show a general uncertainty budget or overview of the contributions, but we don't give a proper uncertainty budget with numbers and anything, because that's again something that each individual laboratory should do by themselves and find out what is enough for your use. So if you need a very accurate measurement, so then you have to have a very good and extensive uncertainty budget. If you can live with a bit bigger uncertainty, so then there could be some contributions which are negligible, but you also need to always know which parts are negligible, so you can't just ignore them without knowing that it doesn't affect your measurement. Then as a last part, so we talk shortly about the calibration of the oscillation type densitometer. For an accurate measurement, you need to calibrate the instrument for traceability and to make sure that it actually measures correctly and which corrections you should be applying. We go through calibration with certified reference materials, give a very basic procedure for the calibration. We give or talk a little bit about the calibration of the temperature cell by another method. For example, with the putting the thermometer in the oscillation tube. And then lastly, so we need to emphasize that if you have some sort of requirements for quality control, you should be, or we recommend you to use an accredited service provider instead of trying to calibrate it yourself. And that was actually the whole structure and the guide. So then I'm also finished. Thank you.
Thank you so much, Pekka. Thank you so much for this presentation. And that's it. We are done with the presentations. I would like to thank all the presenters and to all the participants. And